Hi, I'm Professor Hank Dietz, and welcome to our E-Day 2021 virtual tour of Marksbury 108. So Marksbury 108 is on the first floor of the Marksbury building. Basically up in the front where the windows are here, you'll see a lab that's got lots and lots of windows, and that's us. Next to that lab, you'll see that there's also a machine room, which is also us. We're an electrical and computer engineering lab, and we're also home of the aggregate.org research group, which is basically the name of my group online. Inside the 108 Marksbury EL lab, you would see that we have, first of all, in that machine room, hundreds of PCs that are built into cluster supercomputers. So we have a bunch of large-scale supercomputing facilities there. In addition, you wouldn't really see, but there are actually in the room, many cameras. We use these cameras for computational photography research, where we're actually reprogramming the cameras, building new cameras, etc. We also do an awful lot of things involving making technologies. And you can see here that there's a laser cutter and several 3D printers in the lab. We use those both for making components for our research work and also to develop new technologies to make it easier for people to make things in general. So what do we do in my lab? Well, we're a computer engineering research group, and fundamentally what we do is we build integrated hardware-software systems that we generally make available to the public domain. We make the new technologies available to the public domain. And this is a little bit unusual because we really do have a focus on getting things out the door in a form that the public can use, that engineers and scientists can actually directly make use of in their work. The way that we really do all of our work, and the thing that ties everything together, is not so much the little niche that it's in or anything like that. We seem to span many different niches. What it's really about is our approach to improving computer systems. Basically, the trick is that we try to make the components of a computing system work better together. And if you can do that, that can give you higher performance with no additional cost, and it can also give you new capabilities. So how are we applying that? Well, we're applying it to supercomputers, which we've been doing for many years and we're very well known for doing. We're also applying it to quantum computing now, and we're also applying it for computational photography to cameras. As I said, basically we're working a lot with cameras, reprogramming them, designing new cameras, things like that. We also are trying to improve making technologies so that it's easier for people to produce higher quality parts, more sophisticated things, etc. So let's talk about these in sequence. So for supercomputing, the first thing to say is a supercomputer isn't just an expensive machine. In fact, they don't have to be expensive. A supercomputer is a computer system that can solve bigger problems than an ordinary computer, and it can scale to solve even bigger problems if you have more money to invest in it. Now, the way that that really works is that it's all about parallel processing. A supercomputer isn't faster because it's got very fast processors. It's faster because it has lots of processors. So it can be doing many things simultaneously and thus get a complicated task done faster. So basically, parallel processing can scale up to thousands, millions of processors and give you speed up right now. You don't have to wait for better technologies to develop or anything like that. So this is a huge plus. And of course, if you can do that with parallel processing, you can do that on a small scale and make small supercomputers, systems that have 20 or 40 times the performance of a typical PC, but are still cheap enough that you can actually fit them in an ordinary scientific lab or engineering lab. Our goal in general has been to make parallel processing cheap. So we're not really interested in making the world's biggest machine. We're interested in setting world records for how cheaply you can build a machine that delivers the performance that you need. And we've actually set quite a few world records for that. We also make them do new things, and I'll talk a little bit about that later, but basically it's one of those new things, building video walls, that actually led us into doing computational photography work. Here are a few of our old cheap supercomputers. So you can see this is actually, back in 1994, when my lab actually built the world's first Linux PC cluster supercomputer. That's actually a picture of our first machine with its custom network hardware. This machine here is a machine called CLATU, Kentucky Linux Athlon Testbed 2. And this actually set quite a few world records for price performance. The machine that we built 3 years after that was this machine here, Kentucky Asymmetric Zero. And Kentucky Asymmetric Zero was the first teraflop capable machine in the state of Kentucky, and also set a variety of price performance records. Well, we've continued to do that sort of thing. We've continued to make supercomputing very cheap using clusters and basically all of the available commodity technologies in clever ways that gives you the performance. Here you can see a photograph of the clusters in the machine room of our lab. This is actually a couple of years old. These are a little bit older systems than we have there now, but you get the basic idea that we're essentially taking PC hardware and cleverly connecting the pieces together and giving them a hardware and software environment that allows them to coordinate their actions very efficiently. So you can really solve big problems by spreading them across all of the nodes in a parallel machine. Now, that worked great, and we spent a lot of effort telling the world how to do this too. For example, I'm the author of the parallel processing how-to for the Linux documentation project. Basically, it's the only thing that I've written that lots and lots of people have read. I've got over 200 real publications that are in normal academic places, well-reviewed and all of that. Yet that one document, the parallel processing how-to, has actually been distributed to over 30 million people. And I guarantee you there haven't been 30 million people who've read all of the papers that I've written, or any of the papers that I've written aside from that. So the work that we did in making Linux PC cluster supercomputing available to the world is really something I'm very proud of. It's really changed how supercomputers are built. Except there's a little problem. People have gone nuts in building larger and larger systems. This is a scalable technology, so people scaled up to what I would consider almost insane numbers. So just to give you a perspective, our little machine room has 168 kilowatts of power, which is not exactly a small amount of power. It's about what you would find for example, about 7 high-end houses in the United States. We also have 30 tons of air conditioning. 1 ton of air conditioning is the amount of cooling that you get from melting 1 ton of ice over a period of 24 hours. So you can imagine melting 30 tons of ice every 24 hours just to cool the equipment in our lab. Well, that energy that we're using actually doesn't just go to waste. We actually also use it to heat half the Marksbury building. So in wintry times like it is as I'm speaking to you now, the Marksbury building, half of its heat is actually coming from the waste energy from the machines in our little machine room. The thing that's scary about all of this is that high-end supercomputing has gotten so large scale now that all of the facilities that we have in that Marksbury 108 machine room could not power 1 high-end rack on a top-of-the-line modern supercomputer. Big systems aren't just 1 rack either. There are thousands of those racks. So I had the horrible little realization about 3 or 4 years ago that I'm sort of indirectly responsible for more greenhouse gases than anyone I know. It was never our intent that people would scale these machines up to these ridiculous sizes, but that's what happened. So basically, we made it possible for people to get arbitrary speed up so long as they were willing to invest an arbitrary amount of money. And unfortunately, they've been investing more money and more power than I'm really comfortable with. So what we've been doing in our research now isn't about trying to find more parallelism. It's about trying to make the power consumption be significantly lower per unit of computation accomplished. And by significantly lower, I don't mean a factor of 5 or 10%. I mean factors of 10, 20, 100, or actually the one that we're looking at is about 5 orders of magnitude reduction in power consumption per computation. Now, how the heck can we do that? Well, it takes being a little bit devious, but that's kind of the way we work. We're a very out-of-the-box kind of group. So if we take a look at a very simple piece of code here I have int for a and b. So I'm declaring 2 4-bit integer values, a and b, and then I'm just computing the sum of a and b and putting that into a thing called c. Really nothing clever here. Well, it turns out that simple little piece of code on most modern machines would actually cause at least 160 logic gates to be active in order to compute that result C. In fact, in most machines, it's a lot more than 160, but that's roughly the minimum. Now, why is that the minimum? Well, it's because modern machines try to work on things a word at a time. So if I have an integer A and an integer B, the analysis and all of the things that go on in the compiler, the operating system, and the actual hardware architecture all treat words, machine words, individual variables, as though they were sacrosanct individual things. Well, if we're willing to decompose those words, those values, into individual bit level operations and look at them at the gate level, we can actually get a big improvement. For example, if we just take that sequence and we try to optimize it at the gate level, it turns out that instead of needing at least 160 gates active, it only takes 17 gates to perform this operation. And roughly speaking, power consumption is proportional to the number of gates. So here we're getting an order of magnitude reduction in power consumption just by analyzing things at this lower level, looking at individual bit operations, gate level operations on each of the values. It turns out that we can actually get even more than that. Just using compiler optimization technology, we can actually take other information into account. So for example, here, if I give you the additional information that B is equal to 1, which looks like I'm adding more work to be done, it turns out that the compiler technology, when it's analyzing this, can actually carry that through and simplify this entire computation. So instead of taking 17 gate operations, it takes just 7. Now, I know this seems like this might be some weird little quirk, but in general, the more information the compiler knows, the more it can actually optimize away. So we can replace doing things at runtime with doing things once when the program is compiled, and hence get huge speedups and huge power reductions every time you run the program. Now, how huge can this get? Well, let's take a kind of ludicrous example. So here, I've got a fairly complicated series of operations using 3 8-bit variables, A, B, and C, to produce a new value for A. If we actually generated code for this in the most straightforward way, using these as 8-bit integers, what it would take is approximately 206,669 gate operations in order to do this. All right, and again, remember, roughly speaking, 1 unit of power consumption per gate operation. Well, it turns out that if we actually analyze this particular sequence at the gate level, this is actually not doing anything active. It's not actually doing anything interesting at all. Even though you see these multiplies and adds and so forth, it turns out that whole thing is actually equivalent to saying A equals 0. Now, no compiler or other analysis would have been capable of recognizing that looking at the word level description. If you just look at these word level operations, none of them are redundant, none of them can be eliminated. However, when you break it down to the gate level, things can be simplified to the point where literally we go from having 200 some odd thousand gates to having 0 gates at all, not a single one. Now, obviously, we're not expecting to always get 6 orders of magnitude performance improvement here, but it's possible. And 5 is actually a pretty realistic expectation. Now, the problem is, what kinds of machines are programmed at the gate level? Modern computers don't really work that way, except for one type, quantum computers. It turns out quantum computers are programmed at the bit level, at the gate level. Now, here you see a bunch of pictures of quantum computers, or sort of quantum computers. So let me just say, this is actually one at Google. This one isn't really a quantum computer, but if you've been watching TV, you may recognize this as having been a quantum computer on a certain TV series. This one here is actually IBM's quantum computer. And this one over here is our kind of fake quantum computer. It doesn't actually use quantum mechanical principles in order to perform the computation, but it has very similar properties to quantum computers in terms of how efficiently it can actually perform operations. So let's talk about that a moment. So quantum computing, the real promise of quantum computing is that you can do parallel processing without having to have parallel hardware. So in a conventional computer, if you want to have 1,000 things done in parallel, 1,000 things done simultaneously, you have to have 1,000 processing elements, 1,000 physical things. Well, in quantum, it turns out that there's this wonderful little idea called superposition. So if you have a qubit as opposed to a bit, in other words, a quantum bit can still hold either a 0 or a 1, but the sneaky thing is it can also hold both the value 0 and the value 1 simultaneously. So what you get is essentially you're getting two values simultaneously being held in one bit. Now that sounds like a good savings, but still it's just 2 for 1. Well, it turns out that if you have two bits and they're superposed, and you can entangle them, which basically means that the values of these bits are coupled together, then 2 bits can actually represent 4 values, and 3 bits can actually represent 8 values. And when we get up to something like 16 bits, you can represent 65,536 values in just 16 qubits. So what we're getting is an exponential reduction in the amount of parallel hardware that we need. But we can still actually operate on these values using single operations, single gate level operations. So we basically get parallel operations without the cost of parallel hardware. Now, quantum computers are unfortunately very, very difficult to build and make work. And right now, they're not really at a performance level that's useful to the world. However, quantum computers aren't the only systems that are capable of having something that works like superposition and entanglement. So what we've actually been doing is trying to come up with ways to use conventional computer manufacturing technology, components and such, to build a machine that behaves the same way as a quantum computer. In other words, has superposition, entanglement, and this exponential reduction in the amount of operations it takes to do parallel work. Because if we can do that, we can get an exponential reduction in the amount of circuitry that's active, which means an exponential reduction in the power consumed. So just take a very simple example. With our pseudo-quantum, our quantum-inspired architecture, if we wanted to compute the square root of 29,929, it actually takes us a total of 310 single gate operations on our system to actually compute this value. Well, here's the code that does that. And I'm not going to try and explain all of this. It gets kind of complicated. But let me just basically say that what it's doing is here, this pint h is actually saying, give me all possible 8-bit values. So what it does is, this is a 16-bit value, and it generates all possible 8-bit values, multiplies them by themselves, squares them, and then basically selects which one of those 8-bit values, when squared, actually was equal to 29,929. Very, very simple algorithm, but on a normal computer, this would be very inefficient. Whereas here, we're able to do it extremely efficiently because all of those different values being multiplied together basically are all done simultaneously with relatively little hardware. All right, so not only have we been improving supercomputing performance in terms of speed and cost and power consumption now, but we are also doing things that are basically just brand new capabilities. And as far back as 1994, when we built the world's first Linux PC cluster, actually, you can see it here, it's this unit with 4 displays, we started building video walls to be able to show that these PCs on shelves weren't just PCs on shelves. They were actually behaving as a coupled, tightly coupled parallel system that you could program as one machine. So we started building all these video walls. Well, the video wall that you see over here is from 1996, and it's got a 30 megapixel video wall. 30 megapixel is slightly better than standard high resolution IMAX masters. So basically very, very high resolution. And in 1996, kind of unheard of resolution. So the problem instantly became, well, where do we get interesting images to put on our video walls? So we started to try to improve camera technology because even though people don't think of it this way, cameras are really computers as well. So applying our ideas about improving camera abilities, or I should say about improving computer system abilities to cameras, basically is how you get computational photography. So what we're doing is we're treating cameras as computing systems that can be programmed and can do all sorts of things, some of which don't really look much like what you would expect a camera to be doing. And we use that computation to enhance the abilities of the camera and or to process the data captured to basically achieve new capabilities. We have new cameras, new sensors, and processing models that we've been developing. We have intelligent computer control of capture, for example, reprogramming things like little Canon PowerShot cameras like this here. We also have been doing things where we're detecting or manipulating image properties. So just to give you some quick idea of what sort of thing we've been doing. This is an image that was captured with a Fuji X10 camera, and you can see it's got a very artificial looking blob here, which is basically caused by a sensor defect that whenever it has a very bright spot, it smears that bright spot out over many pixels. This is our computational repair of it. You'll notice that this has a much more natural structure for that point spot, and that's all hallucinatory. It's all completely computer generated, but this allows us to have a much more realistic scene image, looks much more normal, and so this kind of repair is the sort of thing that we've actually implemented. This is actually one that we implemented a while back. Similar kind of thing happened with Sony's RAW format for their high-end cameras. They had a little bit of an error in how they handled some things, and as you can see, it caused some weird artifacts here, which we can repair. We can remove those. You'll also see another artifact from Sony cameras, where occasionally they'll get these thin stripes, these scratch-like marks, and basically we came up with a way to, again, computationally remove those. So this amounts to essentially being able to take an image that has whatever defects and basically computationally repair them by coming up with credible repairs. They're not actually necessarily the scene data that should have been there, but they look good, they look right, they fit. Now, this sort of computational processing is something that we're all getting kind of used to in our cell phones and such, but how about this for another twist on the same idea? If we can use a camera, we can reprogram a camera to do all sorts of different things. Well, we can reprogram the camera to do things that aren't what you would associate with a camera at all. For example, here, we took one of these $80 Canon PowerShots and reprogrammed it so that it would essentially watch very subtle tonal variations in the color of a person's face. Well, these very subtle tonal variations correspond to every heartbeat, every pulse of your heart. So by carefully measuring that, we were actually able to reprogram this $80 camera to be a non-contact heart monitor. So you can see here it's printing out on the display what the heart rate is in beats per minute as it's sampling this, in this case 65 beats per minute. Another example of the kind of thing that we can do, much more relevant to the current pandemic, is that if you really want to stay safe, the key thing is to make sure that you're wearing a mask properly. Well, wearing a mask properly does not just mean that you throw a mask on your face. It means that it has to be an appropriate fit, has to cover both your nose and your mouth. So one of the things that we did was we built some technology that could run on a $100 Android tablet that basically allows it to become an automated scanner that would check to see if the person's face is properly covered by a mask. And you can see we also added a very simple thermal imager, which we built, that allows you to very cheaply determine the temperature. So this could also do a temperature check. Another example of the kind of thing that we've been doing in computational photography is this rather unusual large format camera that we've built. So traditionally, large format cameras look kind of like this, the thing on the left here. And you can see this one's a little unusual because this is an early prototype that we had built where we had a custom 4x5 film holder that actually had a little sensor on it and a little bit of electronics, so we could actually plug this into a USB port and, and actually get a scan of a portion of the scene from that. Unfortunately, building a very large sensor is extremely expensive. So this one just sampled a tiny portion of the scene that was being projected by that lens. Well, in contrast, the camera that we've built just recently, just talked about at the Electronic Imaging Conference last month here, is basically a very high resolution digital camera. It's actually an Internet of Things device. It's completely wireless control. So you can use this basically as a remote webcam. But what it actually does is it uses a tiny little camera on a very simple little board that allows it to capture a 2 megapixel image at whatever location we want by essentially having this control steppers to rotate and move this axially, radially in and out. So what we can do is, believe it or not, we can capture up to 2.6 gigapixel images within the projection of this lens. So we get true high quality, large format images by this very simple scanner. And the punchline is the entire scanner, the entire camera costs less than $100 to build. In fact, if we don't count the lens, it costs less than $50 to build. Now, of course, part of that is that we're doing some very clever things with the computing power inside of here. But more than that, we're actually using 3D printing in a very aggressive way. So here we have a 3D printed linear rail, we have 3D printed body for this, 3D printed focusing mechanisms and so forth. Everything is 3D printed and can actually be built on a cheap commodity printer. In fact, this was actually printed on a $180 printer. So that leads into the last part that I'd like to talk about, and a lot of why we have so many 3D printers and toys like that. We actually build a lot of pieces that are custom hardware, physical hardware, not just computer hardware, in support of our work with cameras and things like that. So we've been doing an awful lot of custom designing and building our own parts. Well, very quickly we realized that that's very hard for most people to do. So what we've been trying to do is we've been trying to automate what's called for design for manufacturability, DFM for short. So basically the idea is to be able to take a design and automatically change that design so that it's easier to build. Intuitively, think of it this way. If you build things out of Legos, we've all used Legos. Legos have those bumps at the top and they don't really come in curves. So if you had a design that requires things to be smooth on the top and has various curves, that's just not something that's easy to build with Legos. Well, most 3D printers have all sorts of things that they can't quite do either. So for example, if you're extruding plastic, that plastic has to be extruded on something that supports it. If it's unsupported, that unsupported span will sag and you'll get a failed part. You'll get a part that doesn't meet your specifications. So what we'd really like to be able to do is automatically change the designs so that they can be printed on a 3D printer. Now, that may not sound like computer engineering. It sounds an awful lot like mechanical engineering. But in fact, it's absolutely computer engineering, and it's compiler design in particular. Basically, a compiler is a piece of computer software that takes a program in one language and translates it into an efficient implementation in another language, basically machine language. Well, if you think about it, a design for a part is really a parametric program, parameterized by things like machine tolerances and such. You have your design, and what we want to do is we want to compile that design into something that the machine can actually use to build it. So basically what we're really talking about here is mainstream computer engineering technology. It's compiler technology, optimizing compilers, much like what we were talking about for quantum computing and all of that. So what sorts of things can we do with this? Well, one of the classic problems is building a hinge. It turns out that if you want to build a hinge, the standard way to make a hinge in normal construction is you'll have a couple of posts and you'll have a bar that goes across. Well, that bar that goes across will generally sag, so that doesn't work. So what we can do instead is we can actually build a fully self-supporting hinge by using this little trick. If we take a look at the little yellow block here, what you can see is that I've got two conic sections. Basically, a cone nested inside of another cone. And this 45-degree angle is sufficient for it to be self-supporting as I lay down each of the layers of this build. So what I get is I can print these little conic hinges pretty much freely, and there's no problem with them because they're fully self-supporting. They're consistent with what a 3D printer can build. So you see a few examples of the kinds of things that you can do with these spanless hinges. For example, here, this is a little fidget spinner that is basically a qubit that we've been handing out as a little keepsake for people to remember that we're doing all this stuff in quantum computing. Here you see something that's actually the most popular 3D printed object that we've created so far, and that's just a hinge box. So this thing prints flat, but all of these are actually hinges done as I've described here. And when you fold it up, you get this little box with the nice UK logo on it. Even more dramatic, but the same exact device, here you see a 3D printed prosthetic hand or a robotic hand that actually has joints which are nothing more than, again, these spanless hinges. In this case, what you have is fishing line run through, and when you pull on the fishing line, that allows you to move each of these joints freely so you can grasp things and release them. All right, so let's take a somewhat fancier example of design for manufacturability. It turns out that you would really like to be able to make things out of more than one component, more than one type of material. But modern 3D printers, generally, the cheap ones at least, can really only print with one material at a time. So what this means is it's very difficult to get different properties out of the same material, but it's not impossible. So there's this concept called metamaterials, which is basically the idea that you can take a single material and essentially, depending upon how you structure it, have completely different properties from that material. In one case, it might be stiff. In another case, it might be springy. In another case, it might be bendable without any springiness. All right. So in 2016, some researchers at the Hasso-Plattner Institute made these metamaterial pliers. And you can see the idea is that as you squeeze in on these parts, the grasp here will come together. And that's all done through this little mesh here, which is supposed to flex. As you can see, I say supposed to flex because, in fact, the flexing is over such a small area that the mechanical stresses build up, and within a few operations, the part fails. Well, let's take a look at our pair of pliers here. Now, this is actually, again, a metamaterial pair of pliers. This is our design. And as you can see, ECE is for Electrical and Computer Engineering, our department. And on the other side, it actually has the UK logo. But the interesting thing is this doesn't just print assembled. This is literally one part. This, if you were to trace it out, actually comes through here, through this spring, then back here, and then that goes around and is connected to here. So this is literally just one material printed as one continuous piece. So it's got all the nice properties of that. However, we get very stiff behavior from this, and because of this overhang-free printed hinge, we can actually have this pivot very freely. The stress is not placed on this pivot point. And instead, we have the springiness here over something that doesn't have to move a whole lot, so it doesn't wear out. It doesn't have material fatigue that causes it to fail. So there are lots of different things that we can do to basically take arbitrarily complicated structures that you might want to build and try and massage the different portions of that so that it's actually easy to build with a cheap 3D printer. All right. Well, I've said quite a lot here, and it spans quite a few different kinds of things, but this is the sort of thing that our lab does, and it makes things really quite interesting because we're not just always doing the same thing. We're using the same methodology, we're using the same approach, but we're always looking at systems as complete systems, trying to tweak the hardware, software, and in fact, the entire system design so that the pieces work better together and get you higher performance, lower power consumption, new capabilities. If you're interested in finding out anything more about my research group, you can contact me, Professor Hank Dietz, at email to hankd@engr.uky.edu. And if you do that, let me just suggest it's a good idea to have the subject line say eDay 2021 so that I know what you're talking about and that I can easily retrieve this from my spam filter if unfortunately email filters it out. I get literally hundreds of emails per day, so it really does help to have an appropriate label on there. The other thing that you can do is you can take a look at agriate.org, our research website. It's not a very pretty site. It doesn't have any flashy graphics or anything like that, but it has a very large amount of stuff there that's really directly usable. In fact, in a typical month, there are close to 2 million hits on our website because we have so many things there that are actually of use to people that you can directly apply. So I would encourage you to take a little look at that or contact me if you have any further questions. So once again, thank you for coming to our little virtual eDay tour. And my apologies that my lab is not actually physically open for this, but hopefully in the near future, we'll be able to get back into the lab. For the past year, as you're probably aware, safety has come first, and it will continue to always be our first issue. So we are not using the lab actively at this point, although all the computing facilities in there are still turned on and we're still actually using them remotely. So hopefully in the near future, we'll be able to start bringing students back into the lab and starting to have more normal functioning. Again, all dependent on safety during the pandemic. So once again, thank you and have a good evening. Stay healthy and stay happy.